Hello and welcome back to another lesson. In this lesson we're going to be talking about oxidation numbers. Oxidation numbers are really important because it's the oxidation number of any particular atom that's going to tell you how the atom is going to interact with some other atom, and that's really the basis of all of chemistry. So oxidation numbers are really important stuff. So let's start out with just a little bit of an introduction. A little background. You know, back in 1869, when Dmitri Mendeleev developed the first really useful periodic table, he used atomic masses to organize the elements on his periodic table. He used masses because the proton would not be discovered by Ernest Rutherford for another 40 years. So his periodic table looked nothing like the modern day periodic table. Now that we understand what protons are, we can organize atoms according to atomic number, because of course atomic number is based on the number of protons each particular atom of a particular element has. The present day periodic table, you remember, uses an arrangement that is based on atomic number, and as of 2006 the periodic table that we're familiar with contains 117 confirmed elements. 90 of these elements, only 90, are found naturally on Earth, and the rest are synthetic elements that have been produced artificially using particle accelerators. As we go through this lesson, anything that you see in red, such as Dmitri Mendeleev in 1869 or Ernest Rutherford, you want to remember that the periodic table is based on atomic number. Anything that's in red is really important and you want to remember it. We're going to start off here by looking at the periodic table. The periodic table is organized, like we said, by atomic number. Hydrogen in the upper left has an atomic number of 1. That simply means, of course, that it has 1 proton in its nucleus. Helium, atomic number 2, has 2 protons in its nucleus. That's important because remember that in the ground state, atoms will have the same number of electrons orbiting that nucleus as they have protons in that nucleus. Why is that important? Because, like I said, we're going to be talking about oxidation number. And oxidation number has to do with the particles in the atom that carry electric charge. The oxidation number itself is actually represented as an electric charge on a particular atom. We'll talk more about that in a minute. The periodic table, like we said before, is organized into 18 groups, a group being a vertical column. Our periodic table here contains in the center of the periodic table what are called the transition metals. In order to simplify our discussion here today, I'm going to simplify the periodic table. What I'm going to do is I'm going to remove the transition metals from our periodic table. And in doing so, we're going to look at a much simpler version of the periodic table, missing the transition metals. But this periodic table should help you understand the idea of oxidation number and how atoms get an oxidation number, how the oxidation number for a particular atom is actually determined. So we're going to look at a simplified version of this periodic table. Our periodic table has groups 1 through 18. Group 1 in the periodic table contains the elements that are in this first vertical column, starting with hydrogen and ending at the bottom with francium, atomic number 87. The groups, these vertical columns, are atoms that have the same number of valence electrons. You want to remember that, that's important. The atoms that are in groups, the same group, all have the same number of valence electrons. For instance, all elements in group 1 That means starting with hydrogen, ending with francium. All of those elements in group 1 have one valence electron, just one. That doesn't mean they all have only one electron. It just means that in the valence level, the highest energy level, remember when we were working on those electron configurations, the highest energy level for each of these atoms has only one valence electron, one electron. All elements in group 2 have two valence electrons. So all of these elements in group 2 doesn't mean that they only have two electrons. For instance, a magnesium atom has 12 electrons because it has 12 protons in its nucleus. But that magnesium atom, like the beryllium atom or the calcium atom and all the other atoms that are listed in group 2, have only two electrons in the highest or outer energy level. That's the valence level. So every atom listed in group 2 has two valence electrons. And every atom in group 13, you notice there's a 3 there, has 3 valence electrons. And if you haven't guessed it already, every atom in group 14 has 4 valence electrons. And every atom in group 15 has 5. Every atom in group 16 has 6. And every atom in group 17 has 7. And then there's group 18. Every atom in group 18 has 8 valence electrons, with the exception of helium. Helium can't have 8 valence electrons because it only has 2 electrons. Horizontal rows on a periodic table, remember, are called periods. Every period ends with a filled valence level. So if you start out with period 1, group 1, with hydrogen, that hydrogen atom you can see here has 1 proton in its nucleus, and orbiting that 1 proton it has 1 electron. 1 proton, 1 electron in the ground state, and that means that that atom is electrically neutral. Remember, protons have a positive charge, electrons have a negative charge, and so the hydrogen atom, as it sits here with 1 proton and 1 electron, is electrically neutral. And the next element, helium, has 2 protons and therefore 2 electrons orbiting it, and those 2 electrons are in its highest energy level, that's the first level, and it fills that first level. So the first period ends with helium and a filled valence level. The second period starts with lithium and ends with neon. It ends with neon and a filled valence level. Lithium atoms in group 1, period 2, all have 1 valence electron. Beryllium atoms have 2. Boron atoms have 3. Carbon atoms have 4. Nitrogen atoms have 5. Oxygen atoms all have 6 valence electrons. Fluorine atoms all have 7 valence electrons. And finally, when you get to neon, the neon atom has a filled valence level with 8 valence electrons. The third period ends with argon and a filled valence level. The fourth period ends with krypton and a filled valence level. And the fifth period ends with xenon, a filled valence level. The sixth level fills with radon, again a filled valence level. And the same for the seventh level. Well, periods fill from left to right. This is important. So let's review what we just said. Each vertical column is a group, and each element within a group has the same number of valence electrons, and therefore it's going to have the same oxidation number. Just keep that in the back of your mind for just a minute. Each horizontal row, remember, is called a period, and each period represents an energy level. Period 1 represents an at represents atoms that have one energy level. Period 2 represents atoms that have two energy levels. Period 3 represents atoms that have three energy levels, and so on. Period 7 represents atoms that have 7 energy levels, and the 7th energy level is the valence level. Period 1, the first energy level is the valence level. Period 2, the second energy level is the valence level. Period 3 have atoms that has only 3 valence levels, and the third level is the valence level. That's how that pattern works. Atoms within each period, remember, fill with electrons from left to right, starting with atoms on the left that have one valence electron, and atoms on the right that have a full complement of electrons in that valence level. Every period ends in group 18 with a filled valence level. That's important. Elements in group 18 are referred to as noble gases, and with the exception of helium, their valence level is a stable octet. That stable octet, that means 8 valence electrons. Stable means those atoms aren't chemically active. Why are they not chemically active? Well, one of the things you'll find out is that they're not chemically active because they have a stable octet or a filled valence level in the case of helium. And they're not going to lose any valence electrons, they're not going to gain any valence electrons. They're stable. Elements like neon and argon can be found in nature as trace gases in the atmosphere. Same with krypton, xenon, and radon. They don't react with any other elements under normal situations because they're stable. They have a filled valence level. Helium, remember, has a stable valence level with only 2 valence electrons. It's the exception in group 18. But it is a noble gas. Why? Well, it has a filled valence level. You'll also notice that on our simplified periodic table, I removed from the bottom of the periodic table, I removed the Lanthanide series and the Actinide series. If you look at this picture, the Lanthanide series and Actinide series fit in where you see this small vertical red line, that line right there. And normally, if you wanted to make this chart wider, you could fit those two series up in there, the Lanthanide series and the Actinide series. On a periodic table such as the one you have hanging on a wall in the classroom, the Lanthanide series and Actinide series are at the bottom of the chart. And the reason they're at the bottom of the chart is really just a matter of saving space. You could print this periodic table with the Lanthanide series and Actinide series slid up into this place where you see this vertical line. But you don't, because if it was in there, that periodic table would be so wide it wouldn't fit on a piece of paper. So most of the time when periodic tables are printed, they're printed with the Lanthanide series and Actinide series at the bottom of the chart. And we're going to leave them out, but just keep in mind that they're really there and they follow the same patterns of electrons that the transition metals do that we just took out of there. We'll talk about those later on. Well, now with all of this preliminary material out of the way, let's go ahead and talk about oxidation numbers. Let me give you a definition. Oxidation numbers help to show the combinability of atoms of various elements. More generally speaking, they just show why atoms do what they do when they come in contact with each other. Why do atoms join together to form formula units? Why do they form molecules? Why do they combine? And in order to do that, I'm going to change our periodic table one more time. I'm going to show you a simplified version of the periodic table, but I'm not going to show you the symbols of the elements. I'm going to show you a Bohr diagram of each of the elements in the first two periods of that periodic table. starting of course with hydrogen, group 1, period 1. Here's hydrogen right here, group 1, period 1. You notice that this hydrogen atom has in its nucleus 1 proton, and orbiting that nucleus it has 1 electron, and that means that as it sits right here, this hydrogen atom is in fact electrically neutral. It's in the ground state. It is electrically neutral. Its electron configuration is 1s1. Its valence level is the first energy level, and you can see that here. It only has 1 energy level, and it has 1 electron in it. So that 1 electron in that highest energy level, its only energy level, is the valence electron. Well, if you jump over to helium, over here in group 18, helium atoms have 2 protons in the nucleus. You can see that right there. They have orbiting that nucleus 2 electrons, and those 2 electrons are in fact its valence electrons. It has 2 valence electrons, 2 electrons in its highest energy level. But now let's go down to the second period. The second period starts with lithium, and all lithium atoms, just like all other atoms in group 1 of the periodic table, that's the first vertical column, have 1 valence electron. And you can see that. You see, just like the hydrogen atom with 1 valence electron, this lithium atom also has 1 valence electron. Well, why is that important? Well, with 1 valence electron, that 1 valence electron represents a very tiny amount of energy. And in the right situation, some atom could actually come along and steal that 1 valence electron. There's its valence electron. In the right situation, this could happen. Something could come along and steal that 1 valence electron. And now if you look at our lithium atom, it no longer has 1 valence electron. How many valence electrons does it have? Its highest energy level is no longer the second energy level. Oh, it's still lithium because it still has 3 protons in its nucleus, but it's no longer got 3 electrons. It only has 2 electrons. And its 2 electrons are now in its highest energy level, which happens to now be the first energy level. Which means, look carefully here, which means that our lithium atom now has the same electron structure as helium in group 18. The electron configuration for helium in group 18 is 1s2, and the electron configuration for our lithium atom now over there in group 1, period 2, is 1s2. Helium and lithium now have the same electron structure. Why did it get that way? Because something came along and took that valence electron away from that lithium atom, leaving it with only 2 electrons orbiting 3 protons. Why is that important? Well, watch what happens. With only 3 protons and 2 electrons, that gives that lithium atom a net electric charge of +1. And that +1 that you see right there, that +1, that is the oxidation number. The oxidation number for any atom is the charge the atom gets, the electric charge the atom gets, by either gaining or losing valence electrons. In this case, our lithium atom lost its valence electron, and that is how it got a net electric charge of +1, and that +1 is the oxidation number. So here's the situation. We now know enough that we can refine that definition for oxidation number. And now our definition looks like this. Oxidation number is the electric charge an atom gets by either losing or gaining valence electrons to have the same stable electron structure as its nearest noble gas neighbor. the nearest noble gas neighbor to our lithium atom here was helium. And by losing one valence electron, this lithium atom gained the electron structure, the stable electron structure of its nearest noble gas neighbor, helium. So our new definition: oxidation number, the electrical charge an atom gets by either losing or gaining valence electrons to have the same stable electron structure as its nearest noble gas neighbor. Well, let's go ahead. Here's our periodic table, simplified periodic table. 2 periods. I'm showing you the Bohr model of the atom. Let's take a look at a beryllium atom. Look at our beryllium atom. Our beryllium atom has 2 valence electrons. I've highlighted them here. It has 2 valence electrons, and then down in the first energy level it also has 2 electrons, so it has a total of 4 electrons to balance the 4 charges of the protons in its nucleus. So as it sits right now, it has a net electric charge of 0. It is electrically neutral. However, what happens if this beryllium atom loses those 2 valence electrons? Now it's going to have the electron structure of its nearest noble gas neighbor. What does that do for the charge of the atom? Well, it has the electron structure of its nearest noble gas neighbor, which is helium, and that leaves it with only 2 valence electrons. It still has the 4 protons in its nucleus. It's still a beryllium atom. And even though it's still a beryllium atom, it picks up an electric charge. And that electric charge that it picks up is +2. 4 positive charges, 2 negative charges. If you add those 2 together, it means that after it lost its valence electrons, it now has an electron structure like helium and a +2 charge. Its electron structure now, by the way, is 1s2, just like helium, 1s2. And that positive charge of 2 that's left over by losing those 2 valence electrons is its oxidation number. The oxidation number of every element listed in group 2 is +2. Why? Because every element listed in group 2 of the periodic table has 2 valence electrons, and it can lose those 2 valence electrons to get an electron structure like its nearest noble gas neighbor, in this case helium, and that leaves it with a +2 charge. Every element in group 2 has the same oxidation number, +2. Well, let's go ahead and look at the next atom on the periodic table. Before we do that, you want to make sure that you understand our definition for oxidation number. Oxidation number, the electrical charge an atom gets by either losing or gaining valence electrons to have the same stable electron structure as its nearest noble gas neighbor. Here's our periodic table. The next element we're going to look at here is boron. And our boron atom has 3 valence electrons. There they are, 1, 2, 3. 3 valence electrons. Our boron atom, as it sits here, has 5 positively charged protons in the nucleus. It has 5 negatively charged electrons orbiting that nucleus, and that gives it a net charge of 0. In other words, as it sits here, it's electrically neutral. However, what happens if some atom comes along and steals those 3 valence electrons, takes them away? Well, now we have an atom that is still boron because it still has the same atomic number. It still has 5 protons in the nucleus. That's what makes it boron. However, we now have an atom that has the electrical structure, the electron structure of its nearest noble gas neighbor, which is helium. If you look at this atom, it has the electron structure of helium. It has lost 3 valence electrons. It now has the 5 positive charges in its nucleus, still has those, but it only has 2 negatively charged electrons orbiting it. It's stable, but it has an electric charge, and the electric charge is +3. Why? Because we have 5 positive charges in the nucleus and only two negative charges, positive 5 plus negative 2 gives you positive 3. And that positive 3 charge, if you haven't guessed it already, that is the oxidation number. Well, let's go ahead and look at another atom. And of course, we want to remember our definition for oxidation number. Oxidation number is the electrical charge an atom gets by either losing or gaining valence electrons to have the same stable electron structure as its nearest noble gas neighbor. Noble gas neighbor, that's important. Remember the last couple of atoms we looked at, the nearest noble gas neighbor was neon. Watch what happens this time. Here's our periodic table. I'm going to skip the carbon atom, which is the next atom in the sequence. In group 14, I'm going to skip that atom. I'm going to jump over to the nitrogen atom. Now I have a reason for doing this, and I'll talk about that in just a few minutes. The nitrogen atom has in its nucleus 7 protons, that's what makes it nitrogen, and it also has orbiting around that nucleus a total of 7 electrons. So our atom as it sits here is neutral. Now I want you to remember only 5 of those electrons are valence electrons. That's what puts this atom in group 15. See the 5 there? Every atom in group 15 has 5 valence electrons. Every single one of them does. And what we said before is that atoms will try to have the same stable electron structure as their nearest noble gas neighbor. What does that mean for nitrogen? It means it needs to have the electrical structure of neon. Neon is only 3 atoms away from nitrogen. If you look at helium, helium is 1, 2, 3, 4, 5 atoms away. So it's going to be easier for nitrogen to get the electrical structure of neon than it would be to get the electrical structure of helium. Why? Because in order to gain the electrical structure of helium, this nitrogen atom would have to lose 5 valence electrons. Well, 5 valence electrons represents a tremendous amount of energy. Instead of losing 5 valence electrons, the nitrogen atom can do something different. It can gain 3 electrons, which will give it the electron structure of neon, like this: 1, 2, 3. 3 electrons gained. And if you count the number of valence electrons now, that means that this nitrogen atom now has 8 valence electrons, just like neon. It now has what's referred to as a stable octet. And so that makes this nitrogen atom extremely stable. Well, let's add up the particles. We have 7 protons in the nucleus. That didn't change. 7 protons, each one with a positive charge. And yet now we have orbiting that, we don't have 7 electrons, we have 10 electrons. That means we have literally 3 extra negative charges orbiting this nucleus. And that gives this nitrogen atom, after it has gained those electrons, an electron charge of 3, an electrical charge of 3. Why? Because it has 3 extra electrons in its valence level. That's what gave it the electron configuration of neon. And so that -3 charge becomes the oxidation number for nitrogen. Well, let's go ahead and we'll take a look at the next element. Remember our definition for oxidation number. Here's the periodic table. The next element in line is going to be oxygen. Our oxygen atom. It's 8 protons in its nucleus and 8 electrons orbiting that nucleus. Now remember, only 6 of those electrons are valence electrons. Only 6. It has a total of 8 electrons orbiting the nucleus. That's what gives it that 0 net charge. That's what makes it electrically neutral. But only 6 of those electrons are valence electrons. Now you have to ask yourself this. What is the nearest noble gas neighbor? Well, obviously it's neon. only a couple atoms away. It only has to gain 2 valence electrons to get the stable electron structure of neon. That's what it's going to do. It has 6 valence electrons. 2 more electrons in that valence level would give it a stable octet, and there they are. So somehow, somewhere, oxygen atoms are out there trying to grab up 2 extra valence electrons to get a stable octet. If you look at the particles in the nucleus, that means that the oxygen atom now has 8 protons in its nucleus and 10 electrons, and that means if you add up the charges, that after all is said and done, with 8 valence electrons, it has a -2 charge. It has 2 extra negatively charged electrons, and you can see them right there. There are those 2 extra negatively charged electrons. Only 8 protons in the nucleus, but it also has 2 extra negative charges, 2 extra electrons, and so it now has the electron structure of neon, a stable octet. But it gives it 2 extra negative charges, so it has a negative charge, and that negative charge of 2, that is the oxidation number. Alright, let's go ahead and look at our next element, and of course that next element is going to be fluorine. Fluorine is in group 17 of the periodic table, and like all elements in group 17, the atoms have 7 valence electrons. Well, our fluorine atom also in the nucleus has 9 protons, and orbiting that nucleus an equal number, 9 electrons, and that gives it a balance of charge. It makes it electrically neutral. Its net charge is 0. It has 7 valence electrons. That's only 1 valence electron away from its nearest noble gas neighbor, which is neon. 7 valence electrons is a lot of energy in that valence level, and so that makes fluorine an extremely reactive element. It's never found by itself in nature. It's always combined with something else because it's very chemically reactive. Very chemically reactive because it only needs to get one more little piece of energy, one more little electron to fill that valence level and give it a stable octet. So it can get it from almost anywhere. It can steal it from another atom very easily. But when it steals that 1 valence electron, it gives it 1 extra negative charge. So here's the particles that make up our fluorine atom after it gets that 1 extra electron. It still has 9 protons in its nucleus, but now it has 10 electrons, and if we add up the charge, that means it now has 8 valence electrons for sure, but a negative charge of 1. And that negative charge, that 1 little extra valence electron, that is its oxidation number, -1. All the atoms in group 17, by the way, are extremely reactive. Why? Because they not only all have 7 valence electrons, but they all have an oxidation number of -1. That's what makes it very reactive. Well, there's only one more atom left in that second period, and that atom is neon. Well, here's the structure of neon. Particle structure: we have 10 protons in the nucleus, each one with a positive charge. We have 10 electrons orbiting that nucleus, which means this atom is electrically neutral. Balance of charge. It also has 8 valence electrons, which is a stable octet. Now that stable octet means that this atom doesn't react chemically with anything else. As a matter of fact, none of the atoms in group 18 react chemically with anything else under normal situations. They are neutral, they're stable, they are inert. And they're that way because they all have a filled valence level. Helium has a filled valence level with 2 valence electrons, and all of the rest, from neon on down, have a stable octet. And by the way, if you see that 0 right there, that 0, that lack of electrical charge, that 0, that's the oxidation number for not just neon, but also every element in group 18. Why? Because they're stable. They have a filled valence level. They're not going to give up any electrons. They're not going to try to take any valence electrons in. They're already stable, and so they have an oxidation number of 0. Remember, atoms will try to have the same electron structure as their nearest noble gas neighbor. Okay, let's go ahead and put all of this now into perspective. Let's look at the relationship between oxidation numbers and valence electrons again. We know oxidation numbers are the electrical charge an atom gets by either losing or gaining valence electrons to have the same electron structure as its nearest noble gas neighbor. In other words, oxidation numbers help to show the combinability of atoms of various elements, and I'll talk more about that in just a minute. Here's our periodic table, at least the first 2 periods of the periodic table. And if we focus just on the number of valence electrons, we know that all elements that are listed in group 1 of the periodic table have 1 valence electron. We know that all elements that are listed in group 2 of the periodic table have 2 valence electrons. We know that all elements that are listed in group 13 have 3 valence electrons. If they're listed in group 14, they have 4. Group 15, they all have 5 valence electrons. Group 16, they all have 6 valence electrons. Every element in group 17 has 7 valence electrons. And of course, the noble gases, they're stable with a filled valence level, and every single one of them in group 18 has 8 valence electrons. That's a stable octet, with the exception, of course, of helium, which is stable with only 2 valence electrons. Well, now if we look at not valence electrons, but if we look at oxidation numbers, we see that every element in group 1 has an oxidation number of +1. It has that because, remember, it loses a valence electron. That leaves it with 1 proton that isn't canceled by an electron. It does that to get a stable electron structure like its nearest noble gas neighbor, in this case helium. So every element in group 2 loses 2 valence electrons, gives it a +2 charge. The charge is equal in value to the number of electrons, in this case, lost. Well, every element in group 3 has a positive charge of 3. It loses 3 valence electrons to have the stable electron structure of helium, its nearest noble gas neighbor, and in doing so that gives it a plus charge of 3. That's its oxidation number. Elements in group 14. Watch carefully. Elements in group 14, like our carbon atom here, well, they're 4 atoms away from helium. Just 4 atoms. So that means that the nearest noble gas neighbor for carbon is helium. Well, yes, it is, half the time. The other half the time, the nearest noble gas neighbor is neon, because it also is only 4 atoms away. So here's the situation. Carbon atoms are in the middle of that period, and every element in group 14 is the same way. It lies in the middle of that period, and so every element in group 14 can have generally a +4 oxidation number or a -4 oxidation number. It can go either way. To the left, its nearest noble gas neighbor is helium. To the right, it's neon. So elements in group 14 can have either a +4 or -4 oxidation number. Well, our elements in group 15 have an oxidation number of -3. Again, these elements from 15, 16, 17, they're going to be gaining valence electrons to get the stable electron structure of their nearest noble gas neighbor, which is neon. So elements in group 15 gain 3 valence electrons to get a stable octet of 8 like neon, and that gives them 3 extra negative charges. So the oxidation number is -3. Well, all elements in group 16 have an oxidation number of -2. They need 2 more negatively charged electrons to have the electron structure of the nearest noble gas neighbor, neon. In group 17, very reactive, because they only need 1 more negatively charged electron to have a stable octet like neon. So they have an oxidation number of -1. And now, of course, the noble gases, Well, they certainly don't need to gain any electrons. They're not going to lose any electrons. They're already stable, so they have an oxidation number of 0. Well, we can take this a little bit further. Look at our periodic table here. This is the entire periodic table. In the middle of the periodic table, we have these transition metals. We left those out up to this point because the transition metals themselves are kind of odd. Most of the valence electrons for the transition metals fall into the D sublevel, and because of that, they're so close in energy that if one of these metals loses 1 electron, it's not very difficult for it to lose 2, or in some cases 3 or even 4. So transition metals have various oxidation numbers, +3, +1, +2, in some cases even +3 or 5. Well, the transition metals, like I said, are pretty odd. We also want to remember that the Lanthanide series fit into this periodic table right there. And because they fit in there, they follow the same pattern as the other elements in that period, in periods 6 and 7. So you have to keep that in mind. Nothing's left out here. So anyway, that's oxidation numbers. It's actually not that difficult to understand if you recognize the patterns. Well, let's take a look again at the transition metals. Well, here are transition metals. And if we look at the actual periodic table, we're going to zoom in on one small part of the periodic table. If you look at this, the periodic table shows the oxidation numbers of the atoms. For instance, scandium atom very commonly has a +3 oxidation number. Well, if you look at titanium right next to scandium, titanium can have some very odd oxidation numbers. It can have a +2, but it can also have a +3 or a +4. See, it has various oxidation numbers, and very often you have to read these off the periodic table or figure them out some other way, like looking at a chemical reaction, to figure out what the oxidation number of that, say, that titanium atom is, or this vanadium atom. Look at the oxidation numbers for vanadium: +2, +3, +4, +5. So the transition metals, remember, can have various oxidation numbers, and oftentimes to figure it out you'd have to look on a periodic table or look at a chemical reaction to figure out what the oxidation number of that particular element is. We'll talk about that certainly in much greater length later on. Let's look at all of this another way. Here's our periodic table again, at least the first 2 periods of the periodic table. We locate our beryllium atom, here it is. We locate our oxygen atom, it's right there. You notice that our beryllium atom has 2 valence electrons. Our oxygen atom has 6 valence electrons. The beryllium atom could lose those 2 valence electrons. Why? To get the stable electron structure of helium. We'll look at that again in a minute. Remember that each of those electrons have a negative charge, so the beryllium atom is losing negative charge, and that's why it leaves it with an oxidation number of +2. Where are those electrons going to go? Well, one place that they possibly could go would be to an oxygen atom, and our oxygen atom could take in those 2 electrons, those 2 negative charges, and that of course would give the oxygen atom an oxidation number of -2. That's the charge the atom gets in order to get the stable electron structure of its nearest noble gas neighbor, which of course for oxygen is neon. So here we have the beryllium atom getting the stable electron structure of helium, and the oxygen atom now has the stable electron structure of neon. Let's look at it a different way. On the left here we have our beryllium atom. You can see the 2 valence electrons there. Remember, they have a negative charge. And on the right hand side we have our oxygen atom. Watch what happens to the electrons. The electrons move from the beryllium atom to the oxygen atom. That leaves the beryllium atom with a +2 charge. it gives the oxygen atom a -2 charge. That's why those oxidation numbers are important. They show the charge the atom gets by, like the beryllium, losing valence electrons, and like the oxygen, gaining the valence electrons. The beryllium now has a +2 charge, the oxygen has a -2 charge. So we have this atom, positive charge on the left hand side, negative charge on the right hand side. What happens next? Opposite charges attract. And so now we no longer have beryllium and oxygen. We now have what's referred to as a formula unit. These atoms stick together because they're oppositely charged. And now we have a formula unit with a net charge of 0. The net charge is 0. That's important. The charge canceled out. And we now have a formula unit of beryllium oxide. This is what happens when oppositely charged atoms come near each other. This is the importance of oxidation numbers. They allow atoms to have opposite charges so that they can attract each other. Atoms on the left side of the periodic table give up valence electrons. Atoms on the right side of the periodic table gain those valence electrons. That gives atoms on the left side of the periodic table a charge that is opposite atoms on the right side of the periodic table, and allows them to attract each other and form formula units, canceling out the charge and forming a new substance, in this case beryllium oxide. But this is for another lesson. The importance of oxidation numbers is that they show why atoms combine to form, in this case, a formula unit of beryllium oxide, or in some cases, molecules.